Hello. Today we talk about sequences of functions and how they are related to like taking limit and integral and convergence and uniform convergence. So let's start. So when we have a sequence of functions like fn, where fn is a sequence of functions and goes from 1 to infinity, where each fn is a function from, say, a subset A to another set B. We say fn converges to F pointwise if for any point x, for every point x in A, fn of x converges to f of x. So for example, consider this sequence of functions. Define fn of x to be x over n. It's a function from R to R, right? So for example, f1 of x is x over 1, which is just x. f2 of x, the second function in this sequence, is x over 2, and etc. Now for any x, fn of x, which is x over n, if we fix x, and if we take limits and send n to infinity, x over n goes to 0, because it goes to x over infinity, which is 0. It means the sequence of maps fn, they converge to constant function 0. So here, this is the function f equals 0 everywhere. That's as a first example. For the second example, we can consider the function fn of x equal x to the n. We can consider this sequence of functions. So we can consider the sequence of functions fn and from 1 to infinity. And we want to see what is their limits. So for example, f1 of x is just x to the 1, which is x. f2 of x is x squared. f3 of x, x cubed, and etc. So we have these sequences, we have this sequence of functions, right? For any x, well, so for example, let's see, if x is 0, fn of x is fn of 0, which is 0 to the n, which is 0. If x is between, say, 1 and 0 on this interval, if we look at fn of the x, which is x to the n, if n goes to infinity, we would have a number which is between 0 and 1, like 1 over 2 to the n, but this power is going to infinity. And when we have a number which is between 0 and 1, when we raise the power, that number would converge to 0, right? If you look at x equal 1, fn of x, which is fn of 1, would be x to the n, which is 1 to the n, equals 1. So it's constant 1. What if x is larger than 1? Then fn of x would be x to the n. X is a number which is larger than 1, like 2. When n goes to infinity, this thing, of course, would go to infinity. So let's see what we've proved up to this point. If you look at the real line R, here we have 0, here we have 1, here we have infinity. If you look at x equals to 0, for this point, fn of x would converge to constant function 0. So when x, so the first case is when x is 0. The limit of the function fn at this point is 0, at just this point. If you look at the points where x is between 0 and 1, which means here, the function again converges to constant function 0. So if you define the limit to be f of x should be equal to, if x is 0, it's gonna be 0. If x is between 0 and 1, it's again going to be 0. The third case is when x is equal to 1. If x is equal to 1, because fn of 1 is equal to 1 for all of them, their limit is, of course, is 1. So f is 1. If x greater than 1, it's going to be infinity. So there is no limit. So it's not defined here because it diverges. This is for non-negative numbers. We can consider the case of negative numbers too. So let's consider the same sequence of maps. So again, fn of x is defined to be x to the n. We want to compute the limit of fn when n goes to infinity. Now let's consider negative numbers. I mean x. Suppose x is a negative number. Well, if x is, well, I mean, there's a reason why we are not doing that. And that's the fact that, well, let's do it. It's okay. So let's consider the case where x is between -1 and 0. Okay, something like -1/2. And we are considering x to the n. So it's going to be negative, for example, if it's -1/2, it would be something like -1/2 to the n. So if you look at this sequence, when n is 1, it's -1/2. When it's 2, it's 1/4. And then when n is 3, it's going to be -1/8, etc. As you can see, this sequence is converging to 0, and that's the case for general x. When x is between 0 and 1, 0 and -1, x to the n converges to 0 when n goes to infinity. So f of x, which we are looking for it, if x is between 0 and -1, it is 0. What if x is -1? If x is -1, fn of x would be fn of -1 is equal to -1 to the n. So this thing would gives us a sequence like -1, +1, -1, +1, etc. And it is not convergent again. So again, there is no limit here. It's not defined. Similarly, if x is less than -1, it would diverge. So it's not defined there. So if we, well, let's give a summary of what we showed. So if we consider the sequence of functions fn of x equal x to the n, if we are looking for the limit of this sequence of functions when n goes to infinity, if we define it f, if we call this limit f of x is equal to, where x is less or equal than -1, it's not defined. When x is between -1 and 1, it is 0. When x is equal to 1, it is 1. When it's greater than 1, again, it's not defined. So that's usually how we can kind of find the limit of a sequence of functions. We usually to start to look at specific points and take limit of the function at those points. Now, something we can do is that we can look at this sequence of functions fn of x equals to the x to the n as a map from the unit interval 0 to 1 to r. Okay, so for example, the first function in this sequence is x, the second one is x squared, x cubed, x to the 4, x to the 5th, etc. So if I look at the graph of these functions, the first one looks like this, goes from 0, 0 to 1, 1. It's y equals x. The second one is y equals x squared. And then if I, for example, this is x squared. Now, if I look at the other functions in this sequence, the way they deform is like this. X cubed would be like this. And then x to the 4 would be like this. And if we compute their limits, if we define f to be limit of fn, f of x is equal to, if x is between 0 and less than 1, it's strictly less than 1, the limit is going to be 0. But if x is equal to 1, fn of x, which is x to the n, would be 1 to the n, which is 1. So the limit of these functions is this function. Maybe it's better to show it with red. This is the graph. Now we can see something interesting here. Although these functions fn, x, x squared, x cubed, etc., although all of these functions are continuous, their limit f, as you can see here, is not continuous. So it is possible to have a sequence of continuous functions like fn, where they converge, their limit is another function f, where this f is not continuous. That is possible. And that's something we usually don't like. We prefer to have a notion of convergence, where when we take limit of a sequence of continuous functions, the limit would be also continuous. That can be a motivation to define uniform convergence. So again, suppose we have a sequence of functions fn. They are defined from a set A to another set B. We say fn converges to f uniformly if for any epsilon there would be a natural number like n, which this number depends on epsilon, such that for all n greater or equal than this fixed number n, well, not fixed, this number depends on epsilon. For all natural numbers n greater or equal than that, fn of x minus f of x By this, I mean the distance between Fn and F. This would be less or equal than epsilon. The important thing here is that this definition in this distance, Fn of x minus f of x being less or equal than epsilon, we have x, but this number n is independent of x. N is independent of x. Okay, so let's look at some examples. So for example, consider, let's look at the examples we already have. In the first case, we defined Fn of x to be x over n, right? And I said, well, this sequence of functions Fn, they converge to the constant function 0. Because for any x, if you look at x over n, which is Fn of x, when n goes to infinity, this would go to 0. This would go to 0. So the limit f is the constant function 0. Okay. Now question: is this convergence uniform? What does it mean? It means, is it true that, well, so we are asking if Fn, which is Fn of x, which is x over n, if this thing is converging to 0 uniformly. Also note that the domain of all functions here is R. So we are considering them as functions from R to R. So is it uniform or not? So suppose it is uniform. Suppose the answer is yes. It means for any epsilon, there exists a number n such that for n greater or equal than n, Fn of x minus f of x would be less than epsilon for any x. Right? Since it should be correct for any epsilon, I take epsilon to be 1. It's just one specific epsilon, right? So there should be a number n for this epsilon equals to 1, where for all numbers n greater or equal than that, Fn of x minus f of x should be less than 1. But Fn of x is x over n. F of x is 0. This number should be less than epsilon, which is 1. Which means x over n, its absolute value should be then 1, should be less than 1. And it means absolute value of x should be less than n for all n greater or equal than n. Is it correct? Is it correct that for every x is less than n for all n greater or equal than n? Is this a statement a valid statement? No. Yeah. So as you mentioned, no, because we can always choose an x which is larger than n, right? Fix any n you want, take any large n. This x, it can be any real number. You can take x to be, I don't know, n plus 1. Of course, that's not less than n. And that's a contradiction. So although x over n as a function of x would converge to 0, but this convergence is not uniform. So no, it is not uniform. So it is only pointwise. Only pointwise. So in some sense, uniform convergence is very fast convergence, or it's very controlled convergence. you can always control the distance between the function fn and f in all points in the domain at the same time. Let's look at the second example. We had, in the second example, we defined fn of x to be x to the n. We consider this as a function defined on the interval 0 to 1 to r. So we saw xn converges to a function f of x, where f of x is equal to 0 if x is greater or equal than 0 and less than 1, and it equals 1 if x is equal to 1. Again, we want to see if this convergence is uniform or not. So question, is this sequence fn converging to f? Is this convergence uniform or not? Again, like the previous case, suppose the answer is yes. Suppose the answer is yes, and this is a uniform convergence. Okay, so it means for any epsilon, there exists a number n, which depends on epsilon, such that for all natural numbers n greater or equal than n epsilon, the distance between fn of x and f of x is less than epsilon for any x in the domain, which here is the interval 0 to 1. Well, take epsilon to be 1. Therefore, there exists an n such that for all natural numbers greater than that, fn of x, which is x to the n, minus f of x, they're going to be less than 1. Okay? Now, suppose x, well, this is supposed to be correct for any x in this interval. For any x in this interval. Suppose x is something that's strictly between 0 and 1. So take some x between 0 and 1. Then f of x would be equal to 0. Therefore, x to the n minus f of x is just x to the n. Oh, I chose bad epsilon. It's better to choose 1 over, I don't know, let's just choose 1 over 100. So it means x to the n would be less than 1 over 100 for every x in this interval, which means x would be less than nth root of 100, again, for every x in this interval. But is it correct? Is every number in this interval less than this thing when n is greater or equal than n? Again, no. Yes, the answer is no, because, well, this number, when n is going, well, when n is very large, so we are fixing some n. The point is that this number, say 1 over nth root of 100, is a strictly less than 1, right? It's a strictly less than 1. So we can always choose a number x between these two, because x can be anything less than 1. And this number itself is less than 1. So we can always find a number between 1 and this number, and that number wouldn't be less than 1 over nth root of 100. So this is also wrong. It is a contradiction. So again, this convergence is not uniform. And actually, that's the reason for this phenomenon, which we are seeing here. X to the n is continuous, but f of x is not continuous. And actually, that wouldn't happen if the convergence is uniform. So that's our kind of important theorem, which I would talk about that. But let's before that look at a few more examples. So question, suppose Fn is a sequence of functions which converges to F uniformly. We usually show uniform convergence with 2 arrows. Also suppose Gn converges to G uniformly. Does it imply Fn times Gn will converge to Fg uniformly? Is it true or not? Think about this question for a few minutes. Does anyone know the answer? Okay, we should either prove it is correct or we should find a counterexample. But since, well, we might not have any specific counterexample in mind, let's try to prove it and we would see what will happen. So let's try to prove that Fngn would converge to Fg uniformly. What does it mean? It means we should show for any positive epsilon, there exists a natural number n which depends on epsilon, such that for all natural numbers greater or equal than that, the distance between Fngn of x minus Fg of x is less than epsilon for any x in domain. Okay. So this is the quantity which we need to Fnx gnx minus fxgx. This is the quantity which we should show it's less than epsilon. What can I do with this number? How can I show this number is small? Remember, my assumption is that Fn converges to F uniformly and Gn goes to G uniformly. So I already know Fn converges to F. So I know Fn minus F is small as I want, and n is large, and Gn minus G is small. The idea is that I want to have factors like Fn minus Fn Gn minus G here, but I don't have something like that. So I should kind of construct these terms. So rather than Fn x Gn x minus Fx Gx, I would write it like this. I will write Fnx Gnx. I would add and subtract this term. Fnx Gx plus Fnx Gx. And then I have minus Fx Gx. So the point is that these two things are equal because these two terms would cancel and we would end up with Fn Gn minus Fg. So they're equal. But the interesting thing is that if we look at these two first terms, we can factor Fnx, and what remains is Gnx minus Gx, which is something which we know we can make it small. And if you look at the second two terms, both of them have Gx. So I can factor Gx, and I would end up with Fnx minus Fx. Again, since Fn goes to F uniformly, I know this thing can be made small. Okay, I know this, what I have here, Fn of x times Gn minus G plus G times Fn minus F is less or equal than the absolute value of the first part plus absolute value of the second part, which is Fn times Gn minus G plus absolute value of G times Fn minus F. And the absolute value of product is the product of absolute value. So this is equal to absolute value of Fn of x times absolute value of Gn minus G plus absolute value of G of x times absolute value of Fn of x minus F of x. But since Gn is converging to G uniformly, I can make this as small as I want. I can make this as small as I want. And I can also make this as small as I want. And I want to kind of make everything small, but there's a problem. If Fn of x and G of x, if these numbers are large, if this is large, or if this is large, yes, you're right, Richard. They should be bounded. If these two numbers are large, doesn't matter how small I make these things, their multiplication still might be large. So as Richard said, the good idea is to assume Fn and G are bounded. So suppose Fn and Gn are bounded. If Gn is bounded, it implies that G also is bounded because Gn is converging to G. That's easy to see. So in that case, Fn is bounded. So say Fn is bounded by, not a good color. Say Fn is bounded by M. Let's say both of them are bounded by M. It would imply G is also bounded by M. So if they are bounded, let me erase these things. Now I can continue my estimation, because if they are bounded by a number like M, it would be less than equal than M times Gn minus G plus G, which itself is less than M times Fn minus F. Now, Gn minus G, I can make it as small as I want. I would make it smaller than, so remember, when we have uniform convergence, we can control this difference, Gn minus G. I can say, look at the numbers n greater or equal than n, such that this difference is less than epsilon over 2m. Okay, same thing for here. I can make this difference as small as I want, say epsilon over 2, or maybe 4m, more convenient. And epsilon over 4m times m is epsilon over 4, and same thing for the second one, and their sum is epsilon over 2. So if you look, what we proved is that this quantity Fn Gn minus Fg at every point x, for every point x, Fn Gn minus Fxgx is less than epsilon over 2 when n is greater or equal than n, which is, so say here this condition would satisfy if n is greater or equal than n1. Say here this condition would satisfy if n is greater or equal than another number, say n2. Here the n which we end up would be the max of n1 and n2, because we want both of these conditions to be true, and that would gives us the uniform convergence. So we need an extra assumption. So if Fn goes to F uniformly, Gn goes to G uniformly, and if they are bounded, Fn and Gn, then Fn Gn would go to Fg uniformly. But if they are not bounded, then it's not correct. If Fn and Gn are not bounded, the theorem doesn't hold. It's not correct anymore. A good example to see, a simple example is this one. Suppose f of x, Fn of x is equal to x plus 1 over n. So Fn would converge to, well, when n goes to infinity, 1 over n goes to 0. So Fn of x converges to just x. And this convergence is uniform. Why? Because Fn of x minus f of x, which f of x is the limit, which is x. This difference is x plus 1 over n minus x, which is 1 over n. And it is independent of x. I can make this difference less than epsilon if n is greater or equal than n, which is, say, the floor of 1 over epsilon plus 1. So the idea in uniform convergence is that we should be able to make this quantity as small as we want, independent of x. To find, so the idea is to find n independent of x. Well, here Fn of x minus x is independent of x. So the epsilon and n and these numbers, they don't depend on x anymore. So this function x plus 1 over n converges to fx equals x uniformly. Now define gn of x to be the same sequence. So fg would be fn gn would be what we have here squared. It would be x squared plus 2x over n plus 1 over n squared. The question is that if this thing converges to fg uniformly, and because f is x, fg is x squared. Now let's see if this convergence is uniform or not. So let's look at fngn minus fg. It's going to be x squared plus 2x over n plus 1 over n squared minus x squared. This difference is equal to 2x over n plus 1 over n squared. Can we make this thing as small as we want independent of x? Of course not. I mean, here we have x. We can just send x to infinity. This thing on the left side would go to infinity. Of course, it's not going to be smaller than epsilon. If n is independent of x, I could just fix an n, which works, and then send x to infinity. The left side would go to infinity. It's not smaller than epsilon. That's a contradiction. So we don't have uniform convergence of the product of two sequences if those functions are not bounded. That's a necessary condition for the theorem. I mean, a lot of times it would work, but in order to prove the theorem, we need that condition. Okay. Let's look at another example. Define fn of x to be x to the n minus 1 over x. Define on the half open interval 0 to 1 to r. Find the limits of f when n goes to infinity, and is this convergence uniform or not? Okay, think about this question for a few minutes. Okay, what is the answer? What is the limit? Does anyone know what is the function this sequence is converging to? Okay, the limit is the constant function 0. And it's actually quite simple because, well, we know when x is between 0 and 1, less than 1, we know x to the n, when n goes to infinity, it goes to 0, right? Suppose, well, an example would be x equal to 1 over 2, something between 0 and 1. And then if you look at this sequence, it would be 1 over 2, 1 over 4, 1 over 8, 1 over 16, etc., which they are getting smaller and smaller. They are converging to 0. So here we have x to the n time over 1 minus x. For any number x, x to the, I can write it as x to the n times 1 over 1 minus x. For any x, this thing is bounded. Well, I mean, not bounded. Bounded is not the correct word to use. For any x, which x is not equal to 1, it's just a constant number. Why? Because here we are taking limit over n, not x. So here I'm assuming x is fixed. It is n, which is changing, and it's going to infinity. And when n goes to infinity, this one goes to 0. So it would be multiplication of something constant with something which goes to 0. The result would go to 0. So f of x equals 0. That's the limit. But now, is this convergence uniform or not? So let's erase these. So the limit is, now we know the limit is 0. We want to see if this convergence is uniform or not. Does anyone have the answer? You're right. For any given n, limit of xn when x goes to 1 would be 1. But one thing you should be careful about is that what is the thing you are taking limit from, right? Here we are not taking limits. So when we are taking limits, you should note, so we have x to the n over 1 minus x. When we are taking limit here, we are not taking limit over x, we're taking limit over n, which means x is fixed here. X is not a variable anymore. For any x in this interval, we set this function x to the n over 1 minus x. For example, x is 1 over 2 or something like that. X is not moving anymore. The parameter which is changing is n. N is the variable here. So it's like checking this thing is correct for any x. So for example, what would happen if x is 1 over 2? That's what we are going to get. 1 minus 1 over 2, which is 2 times 1 over 2 to the n. And then this is the n which we should take limit. Oh, yeah, you're right. So you're answering the second part. That is correct, yes. So about the uniform convergence, yeah, what you're referring to is correct. This is not uniform exactly because of the reason you mentioned. I thought you're still referring to the first part. So yeah, this is not uniform convergence. Suppose it is. Suppose yes. It means for any epsilon, there exists a number n, depends on epsilon, such that for all natural numbers greater or equal than that, distance between Fn of x minus f of x would be less than epsilon for any x in domain. Yeah, it's exactly as you said. Because here Fn, well, say we take epsilon to be 1 over 100. Anything, that's just a random number. So Fn of x would be x to the n over 1 minus x. F of x would be 0, so it would be minus 0. It should be less than 1 over 100, right? Which means 100 times x to the n should be less than 1 minus x. But as you mentioned, now this is supposed to be correct for any x in this interval. So we can make x, we can choose a number x, which is very close to 1. So choose numbers like x, which are getting closer and closer to 1. The left-hand side would converge to 100 times a number which is very close to 1 to the n. So it's kind of getting closer and closer to 100 times 1. Remember now n is fixed. It's supposed to be correct for any n greater or equal than capital N. I fixed one of these numbers n. So the left hand, when x goes to 1, the left-hand side goes to 100. The right-hand side goes to 1 minus 1, which is 0. So it means 100 is less than 0, which is contradiction. So this convergence is not uniform. Okay, is there any question? Is everything good? Okay, then stay safe. That's it for today. Goodbye.